Good morning, everyone. My name is Malcolm Butler, and I'm the Dean of Science here at Carleton University. So today, it gives me a lot of pleasure to welcome everyone to this event, but in particular, Dr. Art McDonald, recent Nobel laureate, and the past collaborators from both Carleton and NRC on the Sudbury Neutrino Observatory collaboration, which was recognized through the award. So first, before we do anything else, I'd like to congratulate everyone involved. We also have a number of guests with us today representing the agencies that supported SNOW's success very much in the past, but are also significant players in the present and future of SNOW Lab, which is the legacy. Particularly, we have Dr. Dan Wayner, who's the Vice President of Emerging Technologies from NRC, Dr. Pierre Charest, the Vice President of Research Grants and Scholarships from NSERC, Dr. Gilles Patry, who's the President of the Canada Foundation for Innovation, Dr. Ken Edgecombe, I believe, is here from the HPCVL, the High Performance Computing Consortium, and Mark Wolf, who's the Chief Technology Officer for Canary. Each of these organizations played a significant, irreplaceable role, in fact, in the past, present, and future of underground science in Canada. So welcome to you all. We're very proud to host this event here today. It's particularly so close to the announcement. And it's a chance for us to recognize the significant contributions of local researchers to SNOW's success, and also of Carleton's ongoing commitment to underground science at SNOW Lab. But without further ado, I know I'm not the one you want to hear speak. I would like to invite our Vice President of Research and International, Dr. Nobel Rajapakse, to come forward to welcome and introduce our guest of honor and recent Nobel laureate, Dr. Art McDonald. Nobel?
Thank you, Malcolm. It's a great pleasure for me to welcome Dr. Art McDonald back to the Carleton University campus. Dr. McDonald is originally from Cape Breton, and he has moved back and forth between Canada and United States over the span of his career. And his last move was the most significant, leaving Princeton University in 1989 to join Queen's University and to take the leadership role of the Sudbury Neutrino Observatory collaboration. Dr. McDonald has deep connections to Carleton University, and it also highlights actually the dedication and the amount of time it takes researchers to achieve results from an extraordinary facility like the SNOW Lab, and which is built and operated 2 kilometers underground. And it helps us to actually understand, provide a very deep understanding of the sun, as well as establish the fact that the neutrinos has mass. Here at Carleton, we actually had a great opportunity to collaborate and provide leadership to the SNOW project, both scientifically and technically, and we are very pleased about that. Our close collaboration with NRC, going back to the first days of the SNOW project, actually led to the development of a unique undergraduate physics program at Carleton, and which we are very proud of. And ladies and gentlemen, you will agree with me that there will be many more years of exciting research that will happen in this facility, and that will actually push the frontiers of science and physics further. But this is also an occasion for us to actually celebrate the distinguished achievement of Dr. McDonald. So please join with me to convey our great appreciation to this significant achievement. And I should also say that what he and the team has achieved is a great thing for Canadian science and technology, because these kind of achievements that are highest at the international stage actually provides the basis for the support of science and technology research in Canada. And so I'm delighted that we have a representative from NSERC, we have a representative from CFI, that without their support, actually, we would not be able to achieve this level of significant achievement. So thank you very much to CFI, and thank you very much to NSERC for supporting this research. And as I said, that it's our great pleasure to have association with Dr. McDonald and this project. And let me now invite Dr. McDonald to the podium to say a few words. Thank you.
So it's really a great pleasure for me to be here today and to share the podium with David, who has been such a leader of this project over many, many years, and also with a whole set of collaborators who have participated in SNO and are now participating in SNO Lab on the future research, which is built on the success of SNO. And I just want you to understand, and that's why I'm here today, that this project is something that was done by an enormous number of people and by many leaders, including David, and so is SNO Lab right now. So let me start by showing you a list of names of the SNO collaboration with the, this is a list of authors, and Carleton and National Research Council are emphasized in red. Of course, it's not just the authors that are responsible for the success. It's all of the technical people, the university administrators, the funding agency people, and of course, all of the wives and husbands and families of everybody who's involved in this. It's a real joint success, and I'm very pleased that, in fact, many people are here today. This was the list as of a day or so ago that David knew, and I've probably missed some individual names, but I'm trying to indicate to you the breadth of participation here at Carleton, which has been an extremely important part of the SNO project, and as you'll hear from David, of SNO Lab as we go forward. I want to pay a special tribute to Cliff Hargrove, who I wish was here with us today. Cliff actually was the person who took the phone call originally from Herb Chen, saying, do you think there's enough heavy water in the reserves in Canada that you could possibly get enough to do this experiment? And that was back in 1984, I believe. And so Cliff spoke to some friends at AECL. I think it was Era Meridian and Jeff Hanna in particular, and they were quite knowledgeable about the science and the potential here, and they set about trying to see if they could get approval for it. George Ewan had been speaking to people already in Sudbury, and Walter Davidson, who is here. Where's Walter? Walter was a part of that as well. They had been looking into the possibility for an underground laboratory way back in the early days. And so it was really a combination of a variety of people who started this off. And there's a picture from back in the very early days. It's from 1986, actually. The group that are listed below this, they're actually the author list from I think the first, this is a proceedings of a presentation that David made at a conference about this idea of trying to do the conference. I think it was the first presentation at a conference that anyone made. And I think that list of about 16 people are the ones who were at the original meeting to found the SNO collaboration. It was founded with Herb Chen as the U.S. spokesman and George Ewan as the Canadian spokesman, and then David, about 6 months later, he was at Oxford University at the time, and he then became the UK spokesman and brought the UK into the project and led them for a number of years before coming back here permanently towards the end of the 80s. So you'll see a number of people who are here that are in the picture. Mort Berkovich is here, and he's second from the left there. George Ewan is third from the right, and Herb Chen is beside him. You can see Cliff right in the center of the picture in the back with a great big smile. David, of course. You can see Davis Earl in the far left, and I understand his grandson is here. There he is. Okay, you look like your grandfather, actually. I can tell. So it was kind of a daunting task at that point to proceed, but there's a lot of people who worked really hard. Walter is not in that picture because he was working hard. He was working with Larkin Kerwin at that point back in Ottawa and had to leave for some meetings. That's why he didn't get in the picture. He was at the collaboration meeting we were holding. We had a lot of very strong people working hard in the founding period, and a lot of strong people from the funding agencies also that got us going on this. Let me now go back to here and talk a bit about the rest of the people who are here. David was a leader here, well, first at Oxford and then NRC, and then here at Carleton when it came to Carleton being the institution that was predominantly working on this in Ottawa. He had a lot to do, put a lot of effort into the original design of the project, and a lot of others were around at that time. Ken McFarlane, who's sitting over here, put your hand up, Ken. I know you don't like to do that, but put your hand up. Ken McFarlane actually was the person who was the principal person to create the engineering design. He was working at Chalk River at that time, and we have what we call the Gray Book, which he put together with an engineering team, which basically set the basis, I think, for this project, and in many ways is just what we built. And Ken is now the engineering director for Snow Lab, and so we're really fortunate to have had his input over many years. And in particular, he and David and the team here at Carleton created the water systems for the project, among other things. But that was a real tour de force because we had to have, and they accomplished it, in the middle of the detector, less than 1 radioactive decay per day per ton of water in the center of the detector, which is non-trivial. It's more than 1 billion times more pure than ordinary tap water. And that was for the heavy water in the middle. Did I get the numbers right? and in the light water surrounding it, there was 7 times as much light water. It was within a factor of 10 of that, even though it was out in the coated cavity where you had radioactivity coming in. Dave was the Snow Associate Director, and we worked extremely closely together, and I really enjoyed that over many years. And so I just want to say thanks. So also many others here on the list, and there are others who are here today who, under the others category, Lauren and Dean actually were students at Queen's, but they now work in Ottawa and are here. And Andre Hamer, who was a student of mine and then a postdoc and who passed away too soon. His wife, Rosalie, and some of his relatives from Europe are here today, too. And there are people apparently on the webcast as well. I hope that Alain, for example, who played a big role here at Carleton, is out there. I can't hear you, but hey. and a lot of other people who worked on this. I'll pick an example of a student. Miriam Diamond was here working with Peter Watson. And Miriam went from here to a very prestigious theoretical physics course at the Perimeter Institute called Perimeter Scholars International, and did extremely well. And she's now working on the Atlas project at the University of Toronto for her graduate work. So one of the wonderful aspects of this, I mean, we started with 16 people, but if you add up all of the people who've been on papers, I think it's 277 authors. And by far the majority of those authors are young people who started working on this project. We have people who worked on this project who are professors at a wide variety of places, Berkeley and Royal Holloway, and Canada Research Chair at Laurentian, and a individual who has just come to Carleton, Marc Boulay, who was a student originally at Laurentian and then at Queen's. He was the person who presented one of the original papers describing the data from the first SNO publication at a Canadian Association of Physicists conference. He then came up with an idea for a dark matter measurement while he was a postdoc at Los Alamos, came back to Queen's as a CRC Tier 2, and now he's a CRC Tier 1 here at Carleton, and carrying on the tradition at Carleton. And and I have the honor to work with him on that project, and he's done a great job. And DEEP is just about ready to turn on for measurement with about 4 tons of liquid argon, and at that point we should have about 10 times better sensitivity than any other existing experiment for dark matter. So there may be another one of these eureka moments for that particular experiment. Dave will tell you about all the other possibilities that SNOLAB is making possible as we go forward. I want to emphasize again, as I've said on the right, the thanks to all the spouses and the families who have supported us over so many years. We all recognize how important that has been to our success, and so thank you. How many people fall in that category that are here today? There's one. And we also want to say thank you to the funding agencies. It was mentioned earlier, but really, I have a list, I think, of the SNO funding agencies. Dave will have another one for the SNOLAB funding agencies, but you can see NSERC, NRC, Industry Canada, Northern Ontario, INCO, which is now Valet, very strong supporter, AECL that loaned us that heavy water for $1, $300 million worth on lease. Ontario Power Generation, who exchanged the heavy water with AECL because we needed heavy water that hadn't had any, the facility had no heavy water that had been in a reactor because you get cross-contamination of tritium. Nortel helped us at their expense for a lot of the electronics that we were building. U.S. Department of Energy, and in the UK, the Particle Physics and Astronomy Research Council. So funding agencies have been great to us. The universities, incredible support we've had at all of the Canadian universities for this project, and thank you very much to all of you for that. I mentioned INCO and Valet, but strong technical staff. The Science and Technology Center here at Carleton is a fantastic place. We on SNO really benefited from that. Steve Tremblay, who was a principal there, actually moved to Sudbury for over a year and was hands-on in terms of making things happen. Put your hand up, Steve. Thanks. Sitting beside him is Morley O'Neill, who did a lot of work as well on the engineering side of things for SNO. And put your hand up, Morley. In fact, everybody who's had a part in this project and should be on the list, and I should have mentioned you, but I haven't. Everybody put their hand up. Let's just see how many. Come on, all the SNO participants. That's a large group of people here, and you can see the way in which Carleton has contributed to this whole thing, and it's really a pleasure for me to be able to come and do this. I'm going to do the same thing tomorrow evening at Chalk River, and so we've had a lot of contributions from a lot of people. So there it is. That's what we built. You've seen probably around here that picture. We could calculate how many times, perhaps, but it's been a real tour de force. It's hard to detect neutrinos. They are the most weakly interacting particles, and so we had to have an enormously big detector way underground, 2 kilometers. It had to be ultra clean. Heavy water was the best material to use to detect neutrinos, and it had some unique properties, which I'll show you a little later. It's the size of a 10-story building. The diameter of that sphere is about 12 meters. Nobody had ever built anything that big before. 10,000 phototubes looking at it, and as I mentioned earlier, the water had to be ultra pure, both the heavy water and the surrounding water. The heavy water is in that blue sphere in the middle, in a great big cavity that was sealed against water, but also against radon gas coming out of the walls. And so that's what was built, and it was built 2 kilometers underground in a very active nickel mine. You often see an article on SNO saying an abandoned mine. Not at all. They're taking thousands of tons of ore out of that mine. Still, they're down almost 8,000 feet, I think, now, and it's still very productive. We are off to the right in that picture in an area which is more stable in terms of the rock, and that was an ideal site. It's deeper than any other site in the world. They are developing one in China that's a little deeper at this point, but right now SNO is still, in terms of a fully operational, SNO lab is now still as a fully operational laboratory, has the best radioactivity levels in the whole world. That reason for doing that is that simply in simple terms, if we hadn't put it 2 kilometers underground, our detector would glow like the atmosphere does for the northern lights for very similar reasons. The cosmic rays that light up the atmosphere would have lit up our detector, and when we did our measurements, we had only 1 neutrino detected per hour, and thanks to the team here, the radioactivity that interfered was at least 10 times lower than that, and well measured. So we were able to see essentially neutrinos and nothing else. So I've been talking about neutrinos, and they are very unusual basic particles. We don't know how to subdivide them, electrons or quarks, any further in terms of basic particles. There are 3 types of each of those. The neutrinos come in 3 flavors, muon, tau, and mu. And they were described in the standard model of elementary particles. It's been so successful, and that was strongly celebrated recently with the ATLAS detector, strong contributions to the discovery of the Higgs, which was the last component in that. They were described as having no mass in that theory, and therefore now, with what we've observed, which is that the neutrinos change from one type to another as they come from the sun, which can only happen if they have a finite mass, that theory has to be modified. And we hope to learn in the process of adding to that theory more understanding of the laws of physics at a very basic level. Neutrinos only feel a weak interaction, so they only stop if they hit the nucleus or an electron head on. And so for them, matter is open space, and they can go through the amount of lead that's equivalent to how far light goes in a year, with only about a 50% chance of hitting something and stopping. So they're very good in terms of trying to get them out of a place like the sun, or these days, in fact, far distances of the universe, because they aren't basically affected by anything. In our case, it was the sun. But then that same property makes them very difficult to detect, and that's why when you build something the size of a 10-story building, you only get them hitting it and producing a burst of light once an hour. And so the challenges were great. Neutrinos are made in very large numbers by the nuclear reactions that power the sun. That's what we detected. They're also made in the atmosphere by cosmic rays, and that's what Super Kamiokande detected. Super Kamiokande observed a oscillation or change of a neutrino type as these atmospheric neutrinos traversed the Earth, and therefore we're very proud to share with them this prize. It was a very significant observation, particularly starting with muon neutrinos. We started with electron neutrinos from the sun and observed a very similar thing in a somewhat different way. What was the major question we set out to answer was what's happening with the neutrinos from the sun, because for quite a few years, starting with Ray Davis's experiment, and Ray Davis and Koshiba received the Nobel Prize in 2002 for being pioneers in this field of particle astrophysics, and particularly for Ray Davis's measurements from the sun. But for 30 years, there had been observation of too few neutrinos, but the measurements that were being made were of the type of neutrinos that are produced in the core of the sun. And so people didn't know whether those calculations, mainly done by John Bacall over many years, whether they were perhaps incomplete or incorrect, or whether, in fact, the other possibility, which would have had strong implications for particle physics, was that the electron neutrinos from the sun were changing into one of the other 2 types in getting to the Earth, and they were eluding detection in the other experiments that were only sensitive to the original type. And so we were lucky with heavy water that we had the ability both to observe the electron neutrinos specifically and also the sum of all the other types. And so the sum of all the other types, even if electron neutrinos are changing into something else, should equal the total flux from the sun. And that's an advantage because you're now measuring the total flux that started in the sun and testing the models that are there telling us how many there should be. So this is what happens. They stream out from the core of the sun. They hit our detector underground, and about once an hour they make a burst of light that we can detect. And because we have heavy water, we're able to observe two different reactions. Heavy water, for a hydrogen nucleus, you see the two H's, the little green things, and the oxygen, has an extra neutron in the nucleus when you have heavy water. And it's that neutron that enables you to measure two processes. This first one, producing the burst of light, is sensitive to all neutrino types. The other one, that is distinguishable, it's a different burst of light, is sensitive only to the electron neutrinos produced in the sun. If you compare those two, and we did, and we found that only 1/3 of the neutrinos of the total are still electron neutrinos. It was very strong evidence that, in fact, neutrinos had changed from one type to the other. And looking at the detector, you can see that the sort of thing you see, the little circles are bursts of light observed in one of the 10,000 photomultiplier light sensors. But at the same time, we're measuring very accurately the time. And so we can measure how long it takes. Well, we can, from the amount of time that it takes in nanoseconds for the burst of light to reach the detector, we can reconstruct where the detector came from. We turn time backwards and look at where that light came from. And in that way, we can observe where in the detector it occurred. So that was a lot of the data that we were working on. And since most of the radioactivity is in the outer area, we could get a very clean area inside the heavy water. A very strong, major construction project. It took us a number of years to do it. Every one of the pieces that we used, over 1 million, had to be transported down in the mine cage, about 3 meters square, something like that. We made the whole laboratory ultra clean. We had HEPA filters. Let's just say the air was very clean, better than a hospital operating room, similar to what you would have in making computer chips. Everybody took a shower and changed into clean, lint-free clothing. We estimated about 70,000 showers altogether over the course of our project, and it's ongoing. There's probably another 70,000 with the work at Snow Lab. You can see the construction was a sphere within a cavity. It was a lot of effort to put it together. Here are the water systems that I mentioned, and here you see on the lower right David explaining to Stephen Hawking about the project when he visited in 1998. INCO designed a special rail car for him and vacuumed him off before they put him in the rail car to avoid having to go through a shower, which everybody else did. And he was very interested. I remember him asking questions of students at that point. You can see in this picture he's got a little clicker in his hand, and he could still use the clicker. He came back to visit Snow Lab 2 years ago, Dave? Something like 3? Yeah. At that point, he could only move his right muscle in his right cheek. And he used that to go through the words on his computer screen and make sentences, and still was very interested in asking questions of people and so on. And he's just an inspiration to everybody that everybody that's met him. And you can see the complexity of the water systems in the upper left. Many Canadian industries brought into helping to develop the technology for this, and that was a value as well. This is the final set of data that we got from the first phase of the project. You see the black circles are the sum of all the neutrinos, and you don't see any radioactivity interfering with it. It's basically neutrinos and nothing else above that energy of about 6 million electron volts. Using properties of those two bursts, we could sort it into two parts. The red points are the points that come from purely electron neutrinos. The blue line is coming from all neutrino types. The green points are from another reaction that is distinguishable because they point away directly as though they had come from the sun. In the next phase of this was the discovery data. This is what enabled us to say neutrinos have changed their type unequivocally. In the next phase of the project, Dave and his team arranged to put in ultra-pure salt, ultra-pure sodium chloride. And that meant that that blue curve was enhanced a factor of 2 or 3, I think, altogether. Anyway, it gave another set of data that then enabled us to get into determining the detailed properties of neutrinos. We've got a very accurate measure of the ratio of electron neutrinos to all neutrino types, as well as of the flux from the sun. So the later phases of SNO were providing detailed, precise data to try to get at the latest additions to the standard model. You can see here that the blue points are all neutrino types. The prediction from the standard solar model is the hatched area, and it fits very well, whereas the electron neutrinos are only a third of that amount. So Dave is now going to speak and tell us about SNOLAB. I'd just like to emphasize a couple of things, some of which I've mentioned before, but as Associate Director, he was very influential in providing leadership in terms of our directions for the project. I mentioned he was the original UK spokesman and very involved in the original design. Ultra-pure water systems, salt additive systems, and then there's one really significant event I want to mention. At one point, we had a real problem. We had a situation where we had high voltage breakdown in the connectors for the high voltage tubes, the light sensors. And Dave looked at this, thought about what the possibilities were, looked at the data, and came to the conclusion that, in fact, we were effectively, by taking the gas out of the water, we were pumping out the volume inside the connectors, which was a very, very astute bit of physics knowledge being applied to this problem. And then within a week, he had figured out that the systems that we had been using to regas the water, in part, could be used to put nitrogen back in, pure nitrogen that came from boil-off from radon, and therefore boil-off from liquid nitrogen, and therefore had no radon. And so we had a solution to a major problem within a few weeks. And everybody in SNO is really indebted to you for that particular time, that particular additional contribution. But in addition to that, David and Carleton led the construction of SNOLAB. Is Daryl Boyce here?
I think he's on the web.
Oh, okay. Daryl, thank you. Dave and Daryl from is it called the physical plant part of the administration here at Carleton, took the responsibility after obtaining the money from CFI and other sources to build SNOLAB. They took the responsibility of building it, and it was built very well. And we are continuing to benefit from this because, as I said, it's still the lowest radioactivity location in the world in a major laboratory. So I will turn over to David to tell you all about that with, if I may, thanks to all of you who contributed to this success.
Okay, so thank you very much, Art, for all your kind words. I'm going to say a few words about where we go from SNO. We've made some discoveries, what comes next. But before that, of course, I want to add my congratulations to Art. It's a wonderful tribute to your leadership. It's great for Canadian science. I serve on many international committees looking at advising labs around the world, and they're all saying this has already had an impact in Spain, in the US, on the world science in this area that we call astroparticle physics. So it's wonderful. And I just want to make one additional comment. Was pointed out to me, in fact, by my daughter, who I think is watching this in Cuba. But there was an article in The Guardian which pointed out an interesting fact, that this prize, the citation for this prize, marks only the second time, at least in the last 35 years, that the collaborations have been identified on the prize. And I don't know how these things work at all, but I have a very strong suspicion that this is ART's doing. And I think it's I think it's a great step, and so I just wanted to make that. So Art has said a lot about the local team. I'm not going to go through what everybody did. We'd be here most of the morning. So I just want to highlight the people. Art has already mentioned Cliff Hargrove, who was originally with NRC and then became part of the Carleton group, and really was an inspiration to all of us with his great enthusiasm and his great skill. And in fact, when I worked out what the problem was with that connector, a very strong element of my thinking was Cliff had tested connectors under high pressure water here at Carleton, and they didn't fail. And I had absolute confidence in his measurement. I knew there had to be something different with the snow water, and that's what led to the measurement. So we're deeply in his debt, and it's a tragedy that he's not here to be with us. But so these are the senior scientists that were involved, and of course the real work is done by the RAs and the students and so on. And we have many of these. I was only going to mention the work of one pair, and they're the first RAs we had on the project. Art has already mentioned Ira's contribution. Ira worked on imaging alpha particles from the decay of the radium that we were extracting from water. And he's gone on actually to a career in industry making medical imaging devices, now with Philips in Israel. And Mikkel was very special too, because we were doing what I considered the world's largest chemistry experiment, and it was all done without chemists until Mikkel joined us, and she is a professional chemist. And so that really transformed what we were doing. It's very much their inspiration, their work, that led to the precision measurement of the background, which was so important. Now, Ira and Mikkel have moved to Israel, but they sent me a note last night saying they were so excited, and I think they're watching us, and their daughter, who was born just as the snow cavity was being excavated, is now a student of music in Israel, and she's composed a song for the occasion. So I think we can have it, and this is Mayan singing it. So if we could...
The Sudbury skies released a downpour of snow, but if you look underground, 2,000 meters below, you'll find that snow lies there too. This team won't melt till they know, until they've shed the light on the mystery of neutrinos. It's a case fit for detectives of the scientific kind, not a smoky New York office, but a sanitary mine. Neutrinos, they are sneaky, they change their IDs all the time, so they must have mass, though they travel light, but they move so fast like they're chasing light. They're elementary, dear Watson, if you catch one, you better hold tight. Could these babies be the matter that we long to find? Could this crack the code of time and space and humankind? Well, there's shafts to go up, to go down, go across, and this full team of miners with McDonald as boss set out to prove at the highest of costs that neutrinos are light and the matter is still in the dark. Could these babies be the matter that we long to find? Could this lift the cloud that is fogging up our mind? Well, there's more to this life than there's waves to the sea, than there's salt to the earth, than there's sugar to your coffee. Everything that we know is just dust and debris when compared to that dark, misty matter we'll never see.
So I think we can... A lovely song and a lovely voice, and so thank you very much. So we, of course, don't only have physicists and chemists. We had a technical team, and I guess Art has referred to most of these people already, and they are just as important, of course, as the physicists in actually achieving what we've managed to achieve. So my topic is what comes next. And we made some very fundamental discoveries with snow. We showed for the first time that neutrinos must have mass. But we had another problem, and at one point it looked like maybe neutrinos would solve that problem, which is the dark matter problem. And what we've learned is, I might say that people who do cosmology didn't like neutrinos as dark matter, but there they were as particles. We knew they existed. At least in some pictures, they had the right mass. Well, we found that that doesn't work. The neutrinos don't have enough mass to be a significant part of dark matter. So what is it? What is this material which makes up most of the gravitational matter in the universe? This is one of the fundamental questions that we have to look at. And neutrinos have mass, but as Art says, it doesn't fit naturally into this beautiful picture we have of the Standard Model. So where does this mass come from? The mass of the neutrinos is millions of times less than any other mass in the of the fundamental particles. Is it a different mechanism that gives them mass? What is it? What is the property of neutrinos, and where did it come from? There's another major line of thinking now that came out of the work of Snow and Super K, and that is we have a mystery in cosmology, which is why are we here at all? If we started with a universe which is a Big Bang, and we have in this enormous state of energy transitions where energy turns into particles and antiparticles, and the particles and antiparticles annihilate back into energy. And this goes on over and over and billions of times, and as the universe expands and cools, and we're left with a state of matter. Where did the antimatter go? Where is there an asymmetry between the matter and the antimatter that gives rise to this? So this is it's a long-standing fundamental problem. And when we learned that not only are neutrinos oscillating, they oscillate in a very big way. They're really all mixed up. And this opens the possibility that the solution to this problem comes from the properties of neutrinos. And this is an idea which has now really taken hold. The entire US domestic particle physics program is working to develop this idea and look and see if they can find evidence that neutrinos have some of the additional properties that would be relevant. But we're also looking at experiments deep underground, properties of neutrinos that could only be measured there to see whether we can shed light on this fundamental problem. So how do we proceed? Well, it was clear that if we had a facility which only could house one experiment, and the nature of these experiments, they take a long time to do all the development work, they take a long time to construct, a very short time to actually get the data, and there's an excitement and there's things happening, and then you move on. If you can only do one at a time, then you have a facility which is exciting once every decade, and in between things are not so exciting, and it's not a facility where you can send your students and expect a culture of excitement and science. Furthermore, there's lots of experiments that need to be done to address these questions that have arisen. And furthermore, I should add, we developed a lot of technology for snow. The whole idea of how do you make a very clean laboratory, how do you make these very clean experiments? What we did in snow was really pioneering. And not only did we find techniques, but we also, I think, encouraged the world, the scientists around the world, to believe that these things are possible. And a lot of people were skeptical when we started. So I think these are some of the things which go in to the next generation of experiments, the technology, the ideas, the questions, the science. So the solution was, we need to build a facility where we can have several experiments in different phases. There's always some exciting science going on. There's facilities to develop the prototypes of the new experiment, to build the big experiments, and carry on as a program. And so we decided that it would be very sensible to expand the facility, both with facilities above ground so that we could support underground activities, and with a much expanded underground facility. This was only possible because of the generous support of the Canada Foundation for Innovation, the Northern Ontario Heritage Fund Corporation, the Ontario Innovation Trust, and of course INCO, our hosts, who made this all possible and made many contributions, most of which don't appear on any balance sheet, but they were huge. So how do we go about it? Well, of course, the first thing you do is an awful lot of filthy, deep, hard rock mining, and here we have the sort of equipment of hard rock mining, the scoops, the drills, the screening going on. The bottom right, I think, is myself checking out the raise bore where we're going to put in a big ventilation shaft to provide the air that we needed for cooling. Somehow we have to go from this filthy environment to a clean laboratory. The inspectors, of course, come down from time to time, and you see here Art and Tony Nobel, who was, of course, part of our group and now at Queen's. It's we do a trade, but the trade is pretty much balanced, and myself and some mine people. So I don't have a lot of time. I just wanted to highlight two of the many experiments that are going on. Well, before I do that, there was one more point I wanted to make. When we designed this surface building, you'll see there's significant parking around. I think we had about places for 40 cars, and I thought this was so crazy, 40 cars coming to Snow Lab? And I'm very pleased to tell people that we've since had to add another 60 places because it overflowed every single day now. So it's been a huge success in attracting large numbers of scientists. You see 20, 30, 40 scientists a day going underground to work on the experiments. It's been a great success. I'm just going to talk about two of the experiments, the two that people here at Carleton are working on. Art has mentioned the Deep 3600 experiment looking for dark matter. The idea is to fill that central sphere with the liquid argon. Liquid argon has a special property that if you put energy into it, it produces light. And so if you had dark matter bouncing off of an argon molecule, it would cause a flash of light in the detector. So the signal looks somewhat, not in detail like what we were looking for in snow, but you surround the detector with light sensors and look for that flash. And when you look at the details of the light, you can distinguish between energy deposited by gamma rays or beta particles, which are your main backgrounds, and possible recoiling argon nuclei, which is the signal you're looking for. This exciting detector is just about to switch on, and we're all looking forward to this. Here at Carleton, we have Marc Boulet, who's already been introduced. He's our new Canada Research Chair, just joined the physics department. We have Kevin Graham, who joined us some years ago. Razvan Cornea, who has also just joined us as a new faculty member. And Art McDonald, of course, is a collaborator on this experiment. And there's a huge collaboration in addition. So we're all looking forward to this as an exciting new experiment about to come on. And, well, this is Kern the Gnome visits DEEP, the DEEP experiment. And the detector is actually now mounted in the left hand of these big steel silos, which are now filled with water to provide the shielding to control the backgrounds coming from the environment from reaching the detector. So there's another experiment we're working on, which is at the moment a dream. It's an experiment aimed at understanding the fundamental neutrino properties and why they might have mass, and also whether we can shed some light on this origin of the universe problem. It's in the planning stage. There are a number of different groups who have ideas on how to do this measurement. There will be a process both in the United States and in Europe, which will select out of these ideas the very best ones. Only the very best will go forward, because these are experiments which are on a scale that everybody can't have their own. They have to be done globally. This is an experiment probably in the $150 million category. We're looking for most of this to come out of the United States, which is very supportive. But we have big contributors from China, Russia, and Europe. But these are experiments which only go forward if they're judged by the world to be the best. And that's what we want at SNOLAB. And I think it's great for the future. And again, the Carleton group is, in fact, the ones from DEEP and myself. I think we should be called the Nobels. This is the Nobel Liquid Detector Group. But it's agreed by all of our collaborators around the world that SNOLAB is the ideal place to do this. It's the best place in the world to mount this experiment, and they're very enthusiastic to come here. So my forecast, well, Canada now has a leading facility for the discoveries in fundamental physics. It has potential world-leading experiments nearing completion or in the pipe. There are real prospects for a repeat of today's event in the not-too-distant future. And our young scientists have a great example to follow in the tireless energy, the enthusiasm, the skill and knowledge of Art. You've set a wonderful example. So congratulations.